Thank you so much to invite me to this event, and I'm really excited because 20 years ago when I joined Ford, there's also a lot of also a lot of people working on the Adams simulation. At the time, there's a joint project between Ford Vehicle Dynamics and Adams. That's on the virtual prototyping Adams chassis. Um, that's a project. Um, for 20 years, there's the Ford is a team continues working on Adams. So it for Adams is really popular in Ford for the vehicle dynamic simulation and the powertrain simulation. So my topic right now is try to introduce the and how do we use the Adams into the powertrain development. So the title is Powertrain in the Loop Simulation with Adams High Fidelity Real-Time Model. Just talk a little bit about our company, Ford Motor Company. We just had uh, we just had celebrate its 117 years anniversary. So for last week, Ford was established in June 16th, 1908. So this it's more than 100 years old, established by Henry Ford. So the very first model is the Model T. Actually, amazing fact is that model has been built for more than 20 years, almost 20 years, with and sold to the world about 14 millions. Actually, it's a 20 horsepower engine, i4 engine, and the sales price is about 260 to 360 range. So about that price, you guess what we can buy today? We just can buy with a lawnmower, $260. So it's just a joke, as a wake up call for me for for this morning. So Ford also produced a lot of exciting products today. And this year we released the Bronco, very excited product, and the Mustang and the Raptor. So I think we can, uh, in the future, we can work together with the MSC to continue to the work stream like the 20 years ago on the Adams chassis, so extended to Adams real time. So my presentation today is talking about focus on the 10 sections. We will talk about the objective background and what is the technical innovation for our powertrain the loop real-time system. And also I want to share with the audience about our schematics of a powertrain field dyno system and our desktop console configurations. Um, More important, I want to share with the team, uh, with the audience about our Adams model overview and the general remarks of the Adams model real-time conversion. Uh, so I think everyone in this event may be very familiar with this the system engineering V-shape because the modern automotive company they develop the process development is to follow this V shape to uh to to roll out their product. So we are starting from the functional design, architecture, system design, hardware component design, and then once we finish the design, we implement the design to the validation, verification, component verification, system verification, or the vehicle validation. So this is for whole vehicle. But for our powertrain, our focus is more on the bottom part. We'll follow the architecture and the system design. Once we receive the requirement, we are follow that path and work on the hardware, develop the powertrain system, and work out the hardware and the software, control software, develop the components, and going back to verify if the powertrain works in the whole vehicle or not. So and also once we confirm it works, we'll put it into the vehicle. We put it into the sheet metal and the skin, and then we verify it in the vehicle. So this is a big iterative process, which costs the time and very and money. So this is our back. We talk about our objective. Our objective is how do we reduce the time for this iteration, and how do we save the cost for this iteration. Remember, if we talk about in the 100 years ago, our product only sells about $260, but nowadays is significantly high. The reasons why, because the powertrain system, the vehicle system getting more and more complicated, and then the development costs a lot of money. So our traditional powertrain integration in the vehicle, we're talking about the B process. We use the real vehicle to do all this tests. So when we do the system verification, we verify control, we need a vehicle. Verification the system, we need a vehicle. Verification the calibration, also we need a vehicle. We drive the prototype vehicle in all over the world, in the proving ground, in Europe, in Asia, in North America, to prove it is robust. This is following the traditional powertrain integration process in the vehicle. So we do need a vehicle put together to confirm the function of the powertrain and the system, powertrain system. However, with the advance of the CAE technology like Adams, so there's a hope. There's a new reality if we can use the CAE model to do the virtual prototyping for the vehicle, while we try to confirm the powertrain functionality and the system robustness. So now we're talking about the system as a powertrain integration in the vehicle, in the virtual vehicle test bed. This is the focus that we want to talk about. So with the same standstill test bed in the lab, we use a simulation program to simulate the vehicle behavior. We confirm the system. We develop the control strategy. We confirm we do the most of the calibration, and also we run the virtual proving ground in the computer. So what the benefit for this is, it is easy. It is easy for us to do the development work. We are not necessarily depend on the weather. We can automate the testing much easier, and we can also development the artificial intelligence, the algorithm, to accelerate the whole process. So what is the technology innovation about this system? So the technology innovation of the system, it is the first of all, we have to for this system, in order to make this system work, we have to introduce the low inertial high dynamic dyno to couple with a high fidelity uh, Adams model. So in the real time. Second technology innovation is we have to improve the vehicle time, vehicle model with a high fidelity model to simplify to make it the real time. So, but at the same time, it should check in the vehicle response to the enough high frequency bandwidth. Otherwise, you lost the dynamics which um, you presented like shuffle, shudder, which you frequently present in the vehicle. So, and also the third innovation and challenge is we have to include the leaf spring, and we have to include the mapping the load grade change, and we have to develop the virtual proving ground to prove out a wide range of the vehicle test applications to replicate the current procedure. So I want to share with the schematics of the powertrain hill dyno system, which we made for the real-time closed-loop simulation for the powertrain. This system, first of all, we notice we have the high fidelity Adams model in real time running the concurrent real-time system. Second one, we have the high performance hill. So this hill is basically combined with the two stack up of the two systems. One is the concurrent real-time PC, and another one is the DSpace PC. So the reason we do such a stack up, it is because concurrent has a really higher speed processor, but however, at the same time, the DSpace has a very convenient user interface, which has been used widely using Ford to communicate with the vehicle vehicle architecture, such as the processor. So we take the advantage of this. We want to take advantage of this convenience. Therefore, we stack the two systems together. When you communicate with the processor, we use the DSpace. When we communicate run the vehicle model with the concurrent. So here and then we have the MADEC system control system, which control the low inertial dyno at a high frequency range, and also we have the dyno control system, so we can control communicate the PCM and all this powertrain control module. And also here we set up the auto test with the script, and we have the host PC to run the script. So therefore, there's three key components. One is the high fidelity model. Two is a high performance hill. The three is a high dynamic dyno. 3H is it's critical for this system. And also, we're talking about it was to introduce the desktop console configuration. There's a operator interface with the control desk, which is in DSpace. We built the system to control the testing. And also, we have that's shown on the left. If you see this console, it's very much similar as what you run in the vehicle. We have tells the engine RPM, we tell you the vehicle speed, and also we also present the output shaft speed of the transmission. we have a uh, 6 different operating modes. We can run the standby, drive away, and also we can use the pedal. You see here, the bottom side, we have the pedal. We can use the pedal to randomly drive the vehicle, to give the calibrator or the tester the real situation um, in the vehicle drive condition. So on the right, there's another screen we call the model interface. This interface completely resides in the concurrent PC, real-time PC, which controls the model behavior. Adams FMU sits on this concurrent, so they do the communication with the D space in the real time through the G form reflective memory. So this model offers the real-time response of the vehicle as you see in the real world. Next, I want to talk about the Adams real-time modeling. So Adams real-time modeling is it is available, the prototype availability, because the challenge is in the vehicle, if we if we want to save the cost, so the company try to reduce the prototype for the transmission test. So the alternatives, we can use the real time to provide the real vehicle response feedback to the engine and the transmission. So therefore, this model needs to be representative to the real vehicle. However, the generic Adams vehicle model has like more than 1,000 degree freedom, which cannot be handled by the real time by any of the computer right now. We have to reduce the degree of freedom from the more than 1,000 to the 100. So the reason to the foundation, how do we reduce this degree of freedom, is just as described by the previous speaker. And what we do is we try check the model frequency. We only keep the model frequency modes and below 50 hertz, and we want to run the model to like 25 to 30 hertz for the transient behavior. So with the model, with the Adams model, real-time model, there's a flexibility, much flexibility. There's a lot of flexibility for us, and we can change the mount tuning. We can change the hardware, and we can change the size of the drive shaft and the head shaft. So this gives us a lot of flexibility for the design study. The Adams conversion from the typical Adams model to the real-time model, there's also a built-in function inside the Adams car, and we are doing that. The most important one is we try to reduce the degree freedom for the leaf spring, because most of the current product in the market is to do with the leaf spring. And also we need to convert the control from the real world and into the wire this control into the the virtual world that communicates with the Adams model. So there's a few more steps, the couple of steps, 3 steps here. We have to reduce the degree freedom and of the model. And the second one, we need to add the additional control, which is communicate with the sensor and the processor. And the third one, we need to extract the trim, and also with the diff, simplify the diff system. There's a steps in the process already inside the MSC software to guide us how to do that. Here's an example for us how to reduce the degree freedom of the Adams leaf spring model. So the typical Adams leaf spring model is a lot of high fidelity and a lot of elements in there. However, because our interesting part is only lower is a frequency up to 40 hertz or 50 hertz, and therefore we work with the Adams team, MSC team, and then we reduce the degree freedom, and then now we created the 5-link model for Adams real-time FMU for the leaf spring. This one is already in the production right now. So there's a process implemented inside Ford for the Adams verification procedure. So we start from the model summary, and we work with the Adams MSC Adams model, and then we integrate the Adams model into the test cell. The timing line is usually you need takes 2 weeks to build a model, and then also we do the offline calibration about 4 or 5 days, and then we have the closed loop engagement test and the model stabilize test for another 2 days, and then we have to run the closed loop dynamic stabilization test. So, and then we deliver the model. This is what we call the model calibration process for the test implementation. Here's the example how do we implement model in the test cell. In the middle, you can see it is our setting of the test in the test cell. The black one, if you see the black one, the black one is concurrent, and the concurrent PC sitting inside the space tower, hill tower. So on the left is the vehicle test, and on the right is what we run the hill. The benefit when we do this, it is if we have the same powertrain and we can use a different model, very quickly switch to the different vehicle instead of waiting too long time to build a vehicle prototype. Therefore, when we go back to the original, if we have the same power pack for this vehicle on the top line, and we quickly just switch the Adams model to represent the behavior of this vehicle, instead of we would build the prototype for each one, which brings us a huge efficiency. Here is some of the correlation, traditional correlation we achieved. The dot line is the vehicle, the solid line, the red line, it is Adams simulation, the hardware in the loop simulation. You can see this is both shift schedule, the step is the shift schedule, and then and this red line is the vehicle speed. Again, here it is this is a 35% of pedal, And that one, the second one is a 50% pedal and the 75% pedal. So you will see the shift schedule follows very good with the vehicle, and then the vehicle speed is also matches very well. The bottom is acceleration, which is most people interested. You will see here the vehicle acceleration follows well with the black line from the vehicle measurement, which is shift quality we are most interested. The peak, you see here the peak level, bottom, peak and the valley, which represent the vehicle. So if you see this difference, we have also puzzled, how do I deliver this project? This is everyone, when you do such a project, you definitely naturally have the question, how do we deliver this project? Because there's impossible to be line-on-line correlation if you run the system like this with the vehicle test. Because there's so many noise in the vehicle test, and there's also the different effects inside the in the cell. We argue this a lot with our calibration team, and I want to share the experience how we finally what we end up with. We discuss with the team because you're not there's impossible to do the correlation one-on-one, and the correlation you can do is finally we decided we use statistics, and then we introduced a software we call the Adams Drive Rating, which is basically create a lot of boxing plot. As long as we are in the forced into the boxing plot, we call it success. So this really helps us to define the success or fail, and then finally, after this, introduce the right metric, and then we get a very good correlation. So otherwise, we always answer. We always in the just like beginning of the project, is how good is good enough, right? Because you are impossible to be line on line. This is a closed loop simulation with the controller. You are out of control. Basically, you are not in control how this environment. So the other choice is you introduce a vehicle simulator. On the left, bottom left is the vehicle simulator. Currently, we're still under construction, so you will see that so this is an ongoing process. We are creating a vehicle simulator. So everything is virtual. Even the proving ground is virtual. Okay, let's. I want to talk about the results. Since we introduced the statistical correlation, and we introduced the AVL drive, and then we can compare all these events, AVL drive versus in-vehicle statistics in the vehicle versus statistics inside the test cell. I want to show what the show on the top of the chart is the what we run the AVL drive rating, the vehicle versus test cell. The blue one is the test cell, and the red one is the vehicle. You will see it's trading very well with the AVL drive rating here, and also we got the overall score is very close. So therefore, I'm able to end up this project. Otherwise, this project is imminent long. Just the people always question you are not line on line with the on top of with the testing. So this is actually most the biggest challenge during our development, which gives us a lot of confidence on the Adams model, and and the whole overall approach. If you look at the shape, the diagram is the spider chart. This is the escape on the left, which is measuring the vehicle, and this is the escape model, which is measured in dino cell. The shape looks like very similar. This is F-150. We're measuring the vehicle, and this is the F-150 measuring the in the cell. So overall, so we have to rely on statistics, not the exact only one test to correlate the model, correlate the system. Once we have this system in place, just give us a lot of freedom. For example, you can do with the model, you can do in the test cell to the trailer toe. So you can artificially define what is the trailer toe slope is, and define the powertrain to check the powertrain capability. So what we did here is we have the flat ground, 7-degree ground, and the 15-degree ground. We just simply in the model, instead of we drive all the way to Colorado to develop this the calibration procedure. So here is the correlation with the vehicle, the testing and the vehicle test in the cell and versus the vehicle. The red is again in the it is the testing in the cell with the Adams model, and then the black one is in the vehicle. You see it is trading very well, especially in the first few shifting events, and after that we don't even care. So this is for flat grade, and this is for 7th grade, and the third one is the 15-degree grade. What I believe, you see there's the gap between the vehicle, real vehicle, and our testing in the engine in the cell. So what I believe it is there's a tire starting slip, a lot of slip right now, and in the model we don't have such a significant slip. So we talk about there's artificial automation and artificial intelligence to develop the powertrain calibration. So we do have inside the Ford, we do have such an effort going on with automation, and here's our result to improve the efficiency. For the same procedure, set of the same procedure, for example, with fairway and a baseline base converter schedule, base coast down schedule, and a wide open throttle shift upshift schedule, and the base downshift schedule, which is a typical procedure we have to complete during the calibration, sensing calibration. In the road test, it takes as about 8 days to complete the whole set. Assuming there's everything smooth, the vehicle is not down. Prototype vehicles also you see the problem of the wiring problem, all kind of problem. The brake is down, everything, and the steering system is not working. So you have to fix the other systems first. But here you don't even worry about that. Assuming every other system is working fine, you need to take at least 8 days to finish. But however, if we use a test cell, we only need 1 day, because everything can be done with the lights off, the automation by the procedure. Therefore, in conclusion, the powertrain dyno testing system have the Ford powertrain transmission team to significantly improve the efficiency up front. It is also facilitating the subsystem tuning process under the well-controlled lab environment, such as cold temperature. So we include the cold temperature cooling cell in there, and we can adjust the temperature all the way down to the minus 40 degrees. The other benefit with the same engine and transmission setting, we can also deploy with the multiple vehicle prototype, right? With the multiple vehicle model, with the same powertrain hardware, we can develop the multiple calibration with the same, just the same setting. So one of them, it is Adams real time is playing the vital role to provide actually the high fidelity model to support high frequency bandwidth shift power dissemination and the transmission system optimization. So this is our conclusion. Our production, the system is already in the production right now. So currently we are gaining high efficiency because of this system. So the last one, I have to acknowledgement to, I would like to express my sincere gratitude to Eric. He's a senior engineer in the MSC software who providing the consistent technical support for during the course of the Adams IT model development. And also I would like to special thanks Dr. Sean Bai. Currently he is an assistant professor in Busan National University of Korea. So he is a PhD from the University of Michigan, and he did a comprehensive assistance to me and a lot of hardworking job during the period of the powertrain heel dyno development. Thank you so much. Thank you very much.